Well, good afternoon and welcome back to Comp 422 and Comp 620, Information Privacy and Security. A couple quick announcements. 1 week from today, there is our first exam. It will be online for everybody, including people who normally attend in person on campus. It'll be an online exam. It's open all day from 6 a.m. until midnight. It should not take you 18 hours to do the exam. But there are people who have only limited time availability, so it's there all day, and you can do whenever you want to. I don't think it'll take you more than 2 hours. I hope it doesn't take you more than 2 hours. Okay. We will not have in-person class on Wednesday, a week from today, during the exam. You should be working on that exam. We will have an online question session starting at the usual 4:30. If nobody's there, if nobody's asking questions, well, I'm going to call it quits. You can always call me, text me, email me if you have questions about the exam. I try to make the questions as clear as I can. I have my TAs review them so we make sure they're all easily understood, but sometimes people have a different interpretation. Contact me if you have a question about the question. Okay, that's a week from today, the exam. Just to make you ready for that exam, there are a couple of assignments coming up. Two-part assignment. One part is you have to sign something and upload it to Blackboard. We will talk about that today with a demonstration. Also, there's a bunch of multiple choice questions, mostly concerning the Bell Laputa model, Windows security, etc. They're easy. Okay. Questions about the questions? Then, moving on, quick review of what we've been talking about before. We talked about multiple types of encryption, in particular symmetric and asymmetric encryption. Symmetric encryption, which AES is the most commonly used symmetric encryption algorithm. Generally, it's a multiple stages where an exclusive orders the key with the data. It goes through the S boxes that substitute values and then rearranges the bits. Permutes the key somehow and does this again. AES does either 10, 12, or 14 iterations through this. And there are instructions in most of the popular processors to do a stage of it, so make it run quickly. And I'm told that you can get 1 billion bytes per second through these systems, probably more. Asymmetric encryption, of which RSA is the most popular, has two different keys. Again, with symmetric encryption, the key to encrypt and decrypt are exactly the same. For asymmetric, they're different. There is an algorithm to create one key from another. So you can't use any sort of bits. With symmetric, you can just pick a random number and use it. Usually you pick a random number, look for really bad cases, and otherwise use a random number. For asymmetric, it has to go through an algorithm to find a key. It's not nearly as fast as AES. AES is fast, RSA is not. It usually involves raising a number to a large power, mod another large number to figure it out. Not only you have to use encryption correctly, but you have to use it effectively. There are several encryption modes, that is, ways to use the encryption. In this diagram, we've got these little boxes here where block cipher encryption, that would refer to an AES encryption. So it takes a block of plain text, encrypts with the appropriate key, and out you come with the ciphertext. Repeats that over and over again for multiple blocks of the plain text. The problem here is that if you have 2 blocks of plain text that are exactly the same, the ciphertext will be exactly the same. And that can give an attacker a lot of information. So this is basically a block cipher mode. There are chaining modes. Cipher block chaining is one of the many. It's pretty simple. Cipher block chaining connects the previous block to the next block. In this example here, for each block, the previous block of ciphertext is exclusive ordered with the plain text. Then you encrypt it like with AES using the key, now it comes from ciphertext. And then that ciphertext goes and it's exclusive over the next block of plain text over and over again. Starts with an initialization vector. Initialization vector is just a bunch of random numbers. It's something to get the system started. You don't have to keep them secret. You just find some random numbers. You need to stick it with the data though, because when you decrypt it, you need to use the very same initialization vector. So the initialization vector that you use to encrypt has to be used to decrypt it. This is the nice thing about the initialization vector is that if you are sending the data twice, the same data, if you use different initialization vectors, all the ciphertext will be different. So it makes it very difficult for somebody to tell what's going on. Another stream or chaining mode for encryption is the Gallows counter mode, GCM. This is the one that's used by Zoom. So right now, all those people online are watching it encrypted with GCM. It's a little bit faster. Well, the big thing is you can do it in parallel very easily because it takes the initialization vector, that becomes the counter. You increment that, and then you encrypt the counter with the appropriate key, same key, and then exclusive of that with plain text, you get cipher. You keep just doing that, incrementing the counter, which is really nice because if you have multiple processors working on this, you know, one process, you have 4 processors, one working on block 0, block 1, and block 2, and block 3, and each one can look ahead. You add just 4 to the counter, and you get the 4th block. So it's very easy to parallelize. Hashing. We talked about hashing for a while. Hashing is where you do a one-way function over the data and produce a number, usually a small number, small meaning 160 bits up to 512 bits. That's much smaller than the text, which might be millions of bits. So you calculate this value over it. And then you can append this to the data. The nice thing about the hash is if any single bit in the text, in the plain text is changed, the hash will be different. And if you encrypt the hash and send it, here's a picture that explains it better. Okay, we start with our message or our data here in green. We hash that using one of your favorite hash algorithms, SHA-1 or SHA-256, whatever you like. And then you encrypt that hash, usually using a private key encryption like AES, although you could also use public key encryption. RSA works perfectly well here, whatever you want. So you encrypt it and you append it to the hash. Okay, this is what you might send to somebody else. They get the message and the hash. They break them apart. They decrypt the hash that they received. And they also, in parallel, calculate the hash of the message they received. They then compare the value they received after decrypted and the value that they calculated. And if they're the same, everything is good. If they're not the same, then we've got a problem. Okay. So that's MAC+. MAC gets you authenticity. It doesn't protect the data. It just makes sure that it hasn't been modified. And you know, not only has it not been modified, but you know where it came from. You know that the person who sent the information must be somebody who had, oh, too bad. It's really, oh. So you know it came from somebody who had the encryption key. Otherwise, you wouldn't be able to decrypt it and wouldn't compare correctly. Okay. All right, so we have a question here. I actually have these. I made the poll questions today, so we're ready for it. There you go. Try that. Hopefully you can see the question. And people in class, get your clickers out and we'll give this. All right. Okay. Put your answer up there. The question? All right. Okay. Sometimes computers don't always do what you want them to do. I've learned that over the 50 years or more. Okay. C is a popular answer, which is good because C is the correct answer. Yes. Oh. They're not the same length of plain text, no. If you wanted to use encryption where you come up with a very random key that's the same length of plain text, that's a very good encryption, but you have to use the key once, it has to be random, and it has to be the same length. Most people, it's very rarely used. Kept secret? No, it doesn't have to be kept secret. Just append it to the beginning of the key, send it along. The other receiver has to know what the initialization vector is. And it's not the same as the key. Okay. Right. There were more people who knew the answer than didn't, but some people were a little confused. Oh, catch you at the next exam. All right. Chafing and winnowing, talked about that a little bit less. It's not used very often. I just thought it was an interesting approach. It uses message authentication codes, MACs, where it sends one bit or maybe one byte at a time and a lot of junk. Every message has a message authentication code. Message authentication code is encrypted. The receiving side decrypts it, checks to see if the code is correct. If it's not correct, they just discard the message. If it is correct, they keep it and append it together. So the sender sends randomly correct codes and junk, and incorrect codes, messages with incorrect codes. Somebody in the middle can't tell the difference. They can't decrypt message authentication codes, so they don't know what's going on. So they're getting a whole bunch of junk, and some of it which is good, but they don't know which is good. So that's an interesting way to send it. Yes. Okay, if you want to send a message to somebody else using this technique, they'd have to know it's coming. Typically, you add a serial number to the messages, which you can, sometimes you add serial numbers and you put serial numbers in the bad messages too, but the receiver knows that at least the messages are always in order, even if there may be a lot of missing ones because they're no good, don't get them reordered. No. And there may be some, this is the beginning of the message. Okay. All right, digital signatures, something new for today. Digital signatures are used very often to identify who created the document, make sure that it is legitimate, it came from who it says. It's supposed to work like a handwritten signature. It does not look like a handwritten signature. It's a bunch of bits. Nobody knows what it looks like. Well, look at what it looks. Nobody cares to see it's a bunch of random binary values. But you want it to work like a hand. It's supposed to be difficult to forge. That is, if you sign something, nobody else should be able to sign it that somebody will think it's true. Easily verifiable. You want the other side to be able to check to make sure that is correct, that they can validate the digital signature to make sure it's not false. Non-deniable, non-repudiation. If you sign something, you cannot then later deny that you signed it, because if only you could have signed it, nobody else could have forged it. Now, if you get a signed document, it must have come from you. That's very useful in contracts. If you want to agree on something, if somebody digitally signs a contract, then you go, okay, they must have really done it. Easy to implement. That, of course, makes it easy. You don't want it to be terribly difficult to do. And you want it to differ from document to document. Otherwise, you don't want somebody to copy it from one place and paste it to the next document and go, ah, it's digitally signed. That won't work. Okay, digitally signed documents do not hide the plain text. They, like Macs, they take the plain text and they will encrypt it, or they do not encrypt the plain text. They make a hash. The RSA, you use RSA typically, so it's an asymmetric system. Digital signatures usually use AES for signature, or excuse me, digital signatures typically use RSA. Media access controls or MACs usually use AES. Oh, too many letters around here. But otherwise, they're the same concept. Okay, how does this work? Well, I got a picture. I like pictures. Okay, here we go. We take the plain text, we hash it with your favorite hash algorithm, SHA-1, MD5, SHA-256, whatever you like, and you get a bunch of bits out of the hash. You then encrypt the hash with the receiver's public key. So if Alice, as always, is sending a message to Bob, Alice will encrypt this with her private key. Alice will use her own private key that nobody but Alice knows. So she encrypts the hash, not the message, the hash, and then appends it to the end of the message, sends it across the network to Bob. Bob gets the message, separates the text and the signature that's attached, decrypts the signature with Alice's public key, which, since it's public, he should be able to know Alice's public key. And we'll talk shortly about effective ways for him to get the public key. Meanwhile, he's got the plain text. He runs it through the same hash that Alice used. So now he has the hash that he calculated, the hash that he received, that he's now decrypted, and you compare to see if they're the same. If they are not the same, you got a problem. That means either it didn't come from Alice or it's been changed somewhere between when Alice sent it and when Bob got it. If it is the same, you can feel pretty confident that it's legitimate. If somebody looks at the message along the way, they can see the plain text, but they cannot change it, because if they change it, the signature won't match. They try to make their own hash, but we won't be able to encrypt it with Alice's private key, because only Alice knows Alice's private key. So the digital signatures verify who sent it. Bob knows that it came from Alice. Programs that you send out over the net are often digitally signed, so you know that the program comes from the people who said it comes from. So you have a program that's supposed to come from acme.com, well, you know it comes from acme.com if they digitally signed it. You know it can't be infected, because if a virus infected, that would change the executable, and then the digital signature wouldn't match, and you recognize it right away. And you can digitally sign lots of things. You can digitally sign jar files, Adobe PDFs, Microsoft Word documents, all sorts of things can be signed. Microsoft allows you to sign things, so do other users. It's used all a lot. Now, a couple of things digital signatures are not. It doesn't look like a handwritten signature. There are systems out there that will ask you to sign a document by using the finger or your mouse to sign it. I bought a car last week, and I had to sign a dozen some documents on the screen electronically. So I got my finger out and signed it that way. Now, this is different. This is not that. And sometimes when you send email, there's something called signature. It's a block of information about, usually it tells you your email address, maybe your mailing address, all this stuff about you, who's your name. And you see at the bottom of somebody's email address, they get to be big things. A lot of times, a lot of pictures and other stuff. And that's your signature. The email systems often automatically add a signature to it when you send it. That's not what we're talking about here. That's something else. So, okay.
I was about to ask, so signature doesn't need to do an extra.
No, a signature, a digital signature doesn't look like a handwritten signature. There are systems that use handwritten signatures, and there are systems that put what they call your signature at the bottom of your email, but those are different. We're not talking about those. Yeah, there are too many things known as signature. I would have called it something else, but I didn't make up that. Did you have a question, sir? Okay, we got it figured out. Yeah, too many signatures. Yes, I bought something that's too many signatures. Okay, if you download a program off the web, you'll often see a box pop up when you go to execute it. Says, wait a second, you got this someplace. And if it's digitally signed, you'll ask you, do you want to run this? If it's digitally signed and the signature does not work, some systems just won't let you run it at all. They just say, nope, forget it. This is bad. Don't even try. Other systems will warn you a lot and let you, if you click yes enough and are persistent enough. But you probably shouldn't do that, because if you get the program that is digitally signed, but the signature doesn't match, and you get this warning message is there for a purpose. Don't run it. So we have another question. Let's try this one. Oh, wait, question about the question. We have a question about this program. Somebody have a question out there?
How's life? Good. You comfortable? If you want another blanket, I got
Okay,
50.
we'll move on then. All right, here is the question.
This wait, no, I am on Zoom. Sorry.
Somebody might want to mute themselves unless they have something to say. Thank you. Can't see your code. Oh, there you go. All right. And over there. Yeah. Oh, you got it. Good. Okay. Let's see what the online people think. Oh, wait. More online people are voting. It's changing a bit. Okay, we got 70% participation online. We had a lot more participation in class. Okay, the answer is C. At least that was the answer I was expecting, C. Max, only protect the hash. It's probably correct. Who made up this question anyway? Okay, I was thinking C because media access controls look very much like a digital signature, but basically the same idea, except one is using a symmetric encryption AES, the other is using RSA. We'll see why. Okay, miserable question. We'll stop this one, just go on. Okay, now, if you're going to use public keys, you have to be able to make sure that the person who's decrypting something that's encrypted with your private key, they have to have your public key. How do they get your public key? And you want to make sure they get the right public key, because if Alice is sending a message to Bob, Eve might come along, send another message, say it comes from Alice, and somehow trick Bob into using her public key instead of Alice's public key. And therefore, Bob will open a message, the key will match, and he'll think it works, but he's got the wrong key. So we got to avoid that. So there are several ways to do this. You can exchange keys. You can give the key to somebody else. You can put it on a thumb drive, hand it to them. That works very well. That's a popular method if you're really concerned about security, is you hand it to them because you assumably know this person. You know, if Alice wants to send messages to Bob, Alice knows who Bob is. Alice walks over to Bob, gives him a thumb drive with the key, and now pretty well assured that nobody got the key in between. As it says here, the government used to do this. The government would send a Marine carrying a satchel over to the ambassador someplace, the embassy of some other country with the key, and then the ambassador would have the key because they knew it, got it from the Marine. Okay, so we have to be sure that people get the keys. And there are basically three ways to do it. I mentioned human interaction. That works very well, but it's slow and it requires physical location. There are key servers and digital certificates. Key servers are pretty simple concept. Key server is a database. You send a message to the key server and you say, I want to know Bob's public key. And the key server sends you back Bob's public key. Since it's public, it doesn't matter. Anybody can get it. It's open to everybody. you may be concerned about, is this really coming from the key server? And we'll talk just a minute how you can be assured of that. When we continue on with some of the concepts here, we're going to need some random numbers, and we're going to need some really random numbers. There are many ways to make random numbers. There are random number algorithms. Most of your computer programming languages have random number generators. There's one in C, there's several in Java. Some of them are good and some of them are pretty miserable. There are cryptographically strong random number generators that work well. They look for information on your system, things that change. A lot of the random number generators are seeded by the current time and date. So that works pretty well. Very hard to tell what the next number is going to be. But if you knew approximately what time the message was generated, and often the messages have a timestamp on them, then you can try the couple hundred milliseconds before and after, and you'll know what it was. You'll be able to detect by only trying a couple thousand tries. So you need really random things, and they look for natural. There are some systems that use real random numbers. You can get a card, plug it into your computer, and it makes real random numbers. It looks like, radioactive decay, looks for the counting the number of cosmic rays that come zooming through your thing, and other things that noise, other things that are really random. Most of us can get by with just calling the cryptographically random number generator in our programming language. You want to make sure it is random. You do this because frequently we'll be using something called a nonce or a nonce. I think it's nonce. A nonce is a random number that's made up and exchanged with somebody else. Frequently, you'll start a message by sending the nonce to the other. Alice will send a nonce to Bob. Bob will encrypt the nonce and send it back to Alice. When Alice gets the nonce encrypted, if she decrypts it, she goes, aha, this is the number I sent to Bob. It's encrypted by Bob. I can decrypt it, so I know that I'm getting a current message from Bob, that it wasn't an old message that's been replayed. So here's where you use your random number generators. So a lot of encryption systems start with a session key that starts by sending these things. Okay. What I'm explaining here. Okay. What was I trying? Who wrote these slides? I think it was me. It wasn't too long ago either. Oh, yes. Sorry, backing up. What I'm trying to do. All right. Here's an example. Say Paul is sending George one or two messages by land or by sea. Now, Benedict, using Paul's public key, can encrypt either message and have the encrypted version. He can't decrypt it, but he can make the encrypted version of the message. And then when Paul sends a message, Benedict cannot decrypt it, but he can compare it to the two encrypted values, tell what it is. So we can determine what the message is, even though he can't decrypt it. That's where session keys come in value, that you put a session key in there and you know that it's current message, not just one that somebody's previously done. Okay. Here's how we do public key requests. There are several ways to do this. So Alice wants to ask the server for Bob's key. We mentioned server. How do you know that it really is the server? So Alice sends a message to the server asking for Bob's key and sending a nonce number 1. And then the server sends a message back to Alice. It's encrypted with Alice's private key or with Alice's key, and it gives back the key for Bob and the nonce. So Alice can decrypt this because it's decrypted with Alice's public key. And they can tell that, in fact, it's the server's key. Sorry, the server's private key. Alice can decrypt it because she has the server's public key. There is a key exchange algorithm, the Needham-Schroeder key exchange algorithm, that you can use to send messages back and forth to a third party. Okay, Alice sends a message to Kathy. She says, I'm Alice. I want to send a message to Bob. Here's a random number. Kathy replies back to Alice, sending Alice, Bob, and the nuns, and a session key that they can use. And the whole thing here is all encrypted with Alice's public key, including part of this message is encrypted with Bob's public key. But now she has the key. Alice can't decrypt this, but she can send it off to Bob, who could decrypt it. Gets, oh, Alice, the key, session key. So then we have a session key. Now Bob can communicate with Alice. Alice can communicate with Bob. They can send the nonce, different nonce back there, encrypt it. Alice decrypts it, sends it back, and now they're assured it's a recent communication. They've got this session key that's shared. They know the key, but nobody else, except for Kathy, knows the key. So you have to assume Kathy's a trusted third party. All right. There's a system that uses this called Kerberos. It's been around for a long time. Well, that's since the 80s. That's getting to be 40 some years now. It's used by Microsoft Active Directory. It's still thought to be very secure. It uses symmetric key encryption, AES. It started with DES, but that was because it was 40 years ago. And it provides a system that allows you to get access to servers. It was first started at MIT, where they had a whole bunch of servers that provided some sort of service, say a file server or a print server, and you wanted to access these. And all the messages over the network were to be encrypted. And this is an encryption system that will allow you to get fresh keys so you could access all the servers on the system with a unique key and nobody be able to decrypt it. We'll go over how this works in some detail. And here is a question that has absolutely nothing to do with computer science, nothing to do with, just see if you're paying attention, or actually, no, who knows? They never mentioned this. What is that? Okay, we have some scholars out there online. All right. People know the Greek mythology. All right. Okay, let's not spend too much time on this because who cares? Remember, I don't grade these things. I don't know the answer. I just want to see anybody knows the answer. Oh, put the cards up to see. All righty, there we are. Okay, gotcha. All right. Okay. Yes, those of you who don't know where this Kerberos thing come from, Kerberos is the name of the hound that protected the entrance to Hades. That way, only dead people could get in, keep live people out in Greek mythology. Hercules went down there to do, I think it was one of the 12 labors of Hercules. He went down there. He lifted Kerberos off the ground. He got his strength from the ground. If he got weak, he could, it was Hercules sort of thing. Anyway, I wouldn't want to lift him up. If you read the Harry Potter stories, the dog appears again in Harry Potter. That's Greek mythology. And Hercules was the one who, yes. Okay, good. Several people. Achilles, who's another Greek hero. No, it wasn't Achilles. Thor is Norse. And Homer just wrote about him. He was real. Okay. Oh. All right. Servers. Okay. Now, in the Kerberos system, the real Kerberos system developed by MIT and not the big dog, but Kerberos has two servers that you need. You need a ticket granting server and an authentication server. So you have two servers. Now, often these server systems are in the same machine, but providing two server functions. In other words, you can send a message to this machine saying, I want to access the authentication server, or you can send a message saying, I want to access the ticket granting server. The authentication server, as the name would imply, validates that you are who you say you are. The ticket granting server gives out tickets, which are encrypted messages or keys that are encrypted and gives you a key. So if you want to go out and access a particular file server, You send the ticket granting server a message saying, I want to access that ticket granting server, and it's set, or actually that file server, and it sends you a ticket that has keys that you can do it. We'll talk about how that works. Everybody's using AES type keys. There is a encryption key known between you and the authentication server. So the authentication server has your secret key that you know, and hopefully nobody else knows except for the authentication server. There's also an encryption key that the authentication server and the ticket granting server know, and nobody else knows except those two entities. Each application server has a key that it knows and the ticket granting server knows, but nobody else. You will not use that secret key between the ticket granting server and the application server, but that will be used for the ticket granting server to send messages to the functioning server to get things done. New keys are created all over the place. To avoid timestamps, to avoid replay messages, all the messages are timestamped. That is, they put the date and time and all the messages. If the system gets a message that's old, longer than how many minutes old, it says, oh, this is not valid, and throws it away. I'm not going to show the messages and all the timestamps and all these messages because just assume it's there. You know it. Okay, here we go. I'm going to use this sort of notation. I've got boxes, do all these graphics, got to use them. All these shows a box that has some data inside, and there's a key that tells you how it was encrypted. This means there's a bunch of bytes, and the bytes are encrypted by this key. You can't see what's inside the data unless you have the appropriate key. Okay, so here's how it goes. A client gets authenticated by the authentication server. Usually you do that in the morning when you log in. It's good for all day. Maybe after 12 hours, you have to re-authenticate yourself. Okay. And then as you want to connect to a print server or something, you ask the ticket granting server for permission to use that, and it will send you the appropriate key. By the way, the ticket granting server can also determine whether you are or aren't allowed to use that resource. That's secondary. Maybe there's a print server that only people from this department are allowed, and people from other departments can't use that, even though they're allowed on the system. No, if you're not a faculty member in the computer science department, you can't print on that printer. Other people print elsewhere. Okay. So here's how we do it. Start of the messages. The user sends a message to the authentication server, AES is authentication server, and it has their user ID. This is the user's user ID or login code or whatever it is, whatever. And one of those nonces. Nonce number one will have several names. We'll call it nonce. So it sends that message. You don't need to encrypt anything. You just send it in plain text, send it to the authentication server. The authentication server replies back to that user and sends a message in two parts. The first part is encrypted in the message, in the key that the authentication server and the ticket granting server shares and nobody else knows. And that includes the user ID and a newly generated key. Remember, this is using AES, so just use a random number generator, makes a new key. It also includes in the message that new key that it just generated, that nonce that the user sent, and this is all encrypted with the key that the authentication server and the users share, that nobody else hopefully besides those two, sends them back. Okay, when the user gets that, they can decrypt the part of the message that is encrypted with their key. They can't decrypt the other part because they don't know those keys, the authentication server, they can't decrypt that. They can save that. You look at this thing, oh, is this the number I sent to the authentication server? Yes, if it is, it's most likely the authentication server. And I save this key because I'm going to need that in a minute. Then the client, the user, sends a message to the ticket granting server, and it includes a portion that was received, the authentication server that was encrypted with the authentication server ticket granting server key. It takes it, just sends it on, and in plain text, it says, well, what application server do I want? You know, what print server, what file server, what I want. Another random number, now it's number two, and the user ID. who am I? My name or whatever you're using for user IDs. Okay. When the ticket grading server gets this, it can decrypt this because it knows that key. They can then check the user IDs. Are they the same? Yes. Okay. And that means that the authentication server really did create this because it's encrypted by the authentication server, and then they have to match. So gotta make sure we got the right person. Then it replies back to the client with the information that the user sent, that's that random number and the name of the server that it wants, and another key. It makes up another random key. Sends that, and it encrypts this with that new key. That was the new key that was sent to the client. Encrypts that. And also sends it a message with another key, the new key, and the user ID with the server's key. This is the key that the ticket grading server and the file server or print server has. So the user can decrypt this because it received that new key just a few milliseconds ago. They can check and say, yep, that's the announce. That was the announce I sent. That's there. And now I have a new key. Save that. It can't read this part, but it can save those bytes, and it sends those bytes over to the application server, the print server, whatever it is. It sends a new random number and its user ID, along with the bytes that it got back from the ticket grading server, that are all encrypted with the key it's shared between the ticket grading server and the application server that the user doesn't know, but it sends the bytes. When the application server gets this, it decrypts this because it knows that key. Nobody else does. Compares the user ID. Yep, that's the user. Gets the new key too. Saves that announce and then sends it back to the user with that key that it just got encrypted that way. The user has that new random number in the key, and that does it. Now we know. Now the user has a key, this new key 2. It can use this and all the messages back and forth to that file server or print server, whatever it is. It's all encrypted with the key that was just created. Everybody knows the keys are new. Everybody knows the keys came from the right source. Nobody can look at anything. Questions about how that works? Yes, sir. Yes. Yes, you have to go to the question was, what about caching? You save the information you got from the authentication server when you first logged in that morning. But every time you go to a new application server, file server, or print server, you have to go to ticket grading server. Once you get that, you keep that key that you're going to use, and then all day you can talk to that print server or file server with that key. Any other questions? Good, that's a good one. Okay, if you all know about it, then go out and count those messages. How many messages were there? You might have to go back and look. I went back to the slide. Count. Ah. Huh. Oh, yeah. Oh, there you go. All right. Oh. Everybody has a different count. It's not an important question. Reason I asked it, the answer is 6. I went back. We can go back and look at that. It is not an important question. But if you go, there's message number 1, sign on the application server. Message number 2, reply from the application server client. Message number 3, ask the ticket grading server. Ticket grading server replies 4. Send a request to the application server. It replies. There you go. Now you're talking. So 6 messages. There is a bunch of messages going back and forth. But the networks are fast these days. So it should be able to do this very quickly. You know how fast the network is. If you're typing something in, say, Google, and as you type characters in, it comes up with suggestions. That's not figuring that out on your own computer. That's sending it off to Google headquarters someplace who's looking in their database, coming up with a guess and sending it back to you. So every time you're doing that, that's back and forth. So it works pretty quickly. So the network runs quickly. Okay, digital certificates. This is a little bit different, but you might see some concepts of Kerberos in the idea of digital certificates. Digital certificates are a means of sending your public key. So if Alice is going to send a message to Bob, and Alice has encrypted the message with her private key, and Bob has to decrypt it with the public key, how does Bob know he's got the right public key? Well, again, we can do personal interaction, go to server, or we can use digital certificates. A digital certificate puts the public key in the message. So we're sending email, when Bob gets the message, he gets Alice's public key. But of course, how does he know that this is really Alice's public key? Well, we have things called certificate authorities. Certificate authorities are out there, and they certificate authorities are companies that sell certificates usually, and they have big certificates, and vendors put their certificate authorities in your computer. So if you have almost any brand of computer, the certificate authority go out there and give you a bunch of certificates. Microsoft does, Apple does, everybody has it. Let's see if we can get out of here. I'm going to try. Okay. Stop sharing. Hang on. Go back to. Please stand by. If we can figure out how this is done. It's not done easily, so we're just going to go back. We'll get there shortly. Oh, I've got something to show you later on. Okay. Oh, doggone. Okay, whoop. We've lost our place. I know where I was. Excuse me. Oh, hang on here. Right there. Come on, computer, you can do it. Why is this not working? Okay. Oh, it's working better than I thought. Okay. Lost. Where is Zoom? I will share. Is that working? Can you see the screen where it says digital certificates and nothing else? Anybody online?
Yes, we
see it.
Okay, sorry. Things got mixed up, but we're okay now. All right, how does this work? So everybody has the public key of certificate authorities. Whole bunch of them. We'll show some later on. I've got something to show you later on. So lots of people have certificate authority keys. Bunch of them. For your favorite certificate authorities, of which there are actually very few in the world, but that's a trust issue that the government, the antitrust people can worry about. Okay, so here's a message. We have the data. So we're sending, let's assume this is an email. This is the email message. There's a checksum of the email message. The checksum, or it's SHA-1 or SHA-255, that is encrypted with Alice's private key. So if Bob wants to check this, he has to decrypt this checksum to make sure it's correct. but he needs Alice's public key. No problem. Here's Alice's public key attached to the message. And how does he know that Alice's public key is good? Well, here's a checksum of Alice's public key, again, SHA-1 or whatever you like, and that's been encrypted with the certificate authority's private key. So Bob can then look at Alice's public key, compute the checksum, decrypt this with the certificate authority's public key, see if they match. If they match, good. You know you've got the right public key, and then over here use to decrypt this so we can check to make sure the message is correct. Okay. You can get more complicated than that. Let's assume we've got a university system and we want to give out public keys to everybody and make sure that all the messages are digitally signed. We start with the department chairs. Department chairs give a private key to each faculty member. Department chair knows who the faculty members are. They just walk down to their office and give them a thumb drive with the key on it. Okay, so all the faculty members have the chair's public key. So if they get a message, they can send a message, they can the hash of the message, sign with their private key. They've got the public key is there, and that's verified by the chair's public key. How do you know the chair's public key is good? Well, the chair gets his key from the dean gets the key from the chancellor. The chancellor knows who all the deans are, he hands out keys to them. The dean knows who all the chairs are, hands out keys to them. And therefore, in this hierarchical method, everybody has keys. And all you really need to know is the chancellor's. Whoa. Somebody out there with a question? Or maybe somebody's out there and should mute their system. Okay.
Yeah, just write a check. Just
Oh, I can't hear what you're saying.
$11,000. She was 26.
Okay.
Anyway, limited value.
Let's mute yourself, please. Whoever's making noise. Thank you.
On the hood, hit the windshield. Then when he hit the brakes,
Okay, could you? Well, I could mute you if you had.
but she is dead.
There. Take that. Yes. It starts at the chancellor's office. The chancellor has, and you only need to know the chancellor's public key because you can find out all the other. So if you get a key, again, the chancellor gives them to the dean gives them to the chair gives them to the faculty. So everybody's got a key. So you can. Oh, yeah, okay. Then you got to reset that portion of the tree. That is a complication. There's a talk about that in a minute. We have to revoke their key. That idea is coming up shortly. Good thought though. But you just need the dean because if you put all this stuff together, then you have all these keys, and all you need is a chance because we take the chancellors to verify the deans to verify the chairs to verify the faculty, and that faculty can verify the data. So it seems like a lot of processing, but that way you only need it. And of course, once you have the chair's public key, you don't throw it away, you keep it. Okay, another question. Why? Oh, back up, hang on. Oh. Zoom is. Oh, Zoom is not working for me. How about that? Oh, now we're going. Okay, there we are. Always a gotcha. Oh, CAA, certificate authority. Not kind of word, telephone. Certificate authority. twist it around. Oh, that, now hold it the right way so I know what you want. Hold up. Oh. There's and there's, okay, we got them all. All right, okay, the folks online got it after I figured it out. Popular answer is B, yes. The certificate holds the public key of the owner. Everybody's supposed to know the public key of the certificate authority that's provided by external means. So yes, the answer is B. Okay. Don't have not going to pass the private key because only the owner keeps that private key. Okay. There are standards for this, of course. All the certificates come in a particular format so that other systems will recognize it. It's X.509 is the name of the standard. The International Telecommunications Union, which does a lot of networking standards, all of them are X dot something. So there's lots of them out there. Needless to say. And this one's used for certificates, which is used for, HTTPS. We have the secure version HTTPS, transport layer security, that's TLS. All that uses certificates. The certificates are used so that you can validate who is sending this. So the initialization of the transport layer security or HTTPS, when you log on to the server, it's going to send its certificate to you, giving you its key. And you can look in the certificate and see, is this really who I think it is? If I went to the www.acme.com website and I get a certificate, it better say acme.com on it, or I'm not going to accept this. There are companies that sell these. Certificate authorities usually sell certificates. You can go out there and buy them. You can get them for free. There are several places you get them free. I just Googled up a couple here that I found. I'm not advertising for these people, but they're out there. Now, the ones they want for servers, they usually charge quite a bit because it takes them milliseconds to make a bunch of bits, and then they sell this bunch of bits for hundreds of dollars. Nice job if you can get it. I think most of what they're selling is the insurance that it works. Oh, okay. Well, Fine, you should ask. Okay, certificate authorities. You can look on they are used to sign things. So I have a digital certificate that I purchased from one of these companies. I spent money on it. And I digitally sign some emails and sometimes encrypt emails of the other person. My wife has a digital certificate. I have a digital certificate. And since I teach cybersecurity and I'm really paranoid, every time I send a message to my wife, which are usually very dull, but when I send it to her, I sign it and I encrypt it. My computer has her digital certificate. Her computer has mine. So I encrypt it with her public key that I have, and I encrypt the message with my private key. She gets it. She can decrypt it with my public key that she has, other way around. And she can also check the digital certificate. So we share the digital certificates. Right, yes. But again, if you go out on your computer, we'll see this in just a minute. Yeah, we've got plenty of time. On Microsoft, there's things that shows you, these are trusted root certificate authorities that you might have, certificate authority. Dr. Shu is in here. Yes, he's got a certificate. I trusted his certificate so we could do things together. The certificate, it will tell you this is not a trusted certificate, that this certificate is. Yes, good point. Because what happens is your certificate is signed by the certificate authority. We don't have a picture of that. We're going to get to a picture that shows that. Yes, and so you know that your certificate is valid, and other people know the certificate is valid because it's signed by a certificate authority, and they know the certificate authority's public key. Every now and again, I used to deal with somebody, and they'd send me a certificate signed by a certificate authority that my system didn't know. In particular, if I was doing some work for the government, somebody had sent something from the government, it'd be signed by a government certificate authority. The government has their own. They don't require Microsoft to do something for them. And so they have the certificates, and I would decide to trust the certificate authority of the government. I'm not really sure I trust the government, but I trust the certificate authority of the government, particularly when I knew this person was supposed to be sending me an email. I expected it to be signed. So I had great confidence that was correct. Okay. Now, every now and again, somebody might leave the organization, or somebody might discover the secret key of their, break into your computer and have that information. And you want to go, I don't want that certificate good anymore. I want to get rid of that. So the certificate authorities have certificate revocation lists. They have a list of certificates that are no longer any good. And when you receive a certificate, say you're starting a message with HTTPS and you get the certificate from the company, you should go out to the certificate authority and check, is this certificate still valid? And if it says it is, then you go with it. Otherwise, if it says it's been revoked, you should not use it. Now, it's been shown that a lot of programs do not do that step. That's an extra step to check to see if the certificate is valid, but it's very useful to do. Several years ago, somebody went to a popular certificate authority and said, hi, I'm Microsoft, I want a key. And the certificate authority gave them one. It said Microsoft. Real Microsoft was quite upset about that. The certificate authority, of course, immediately put out a revocation message and put them on the revocation list that this certificate is no good. And Microsoft sent out messages to everybody saying, don't trust this certificate. They were upset, I believe. But it's used to withdraw privileges. So there are revocation lists, because checking is not mandatory, but it's a very wise thing to do. Also, certificates have expiration dates. After a while, they get old. I think that's just so the certificate authorities can sell you a new one. But they have revocation dates, and if they get old, they don't work anymore. So you have to get a new one. There are, of course, problems with revocation lists. What if at that moment you cannot access the certificate authority? What if their website is down, or somewhere in the middle, the network is broken, somebody with a backhoe dug up a cable, then you might not be able to get there. Also, of course, sometimes it doesn't always work. And the certificate authorities can be subject to attack. We'll talk about denial of service attack, but somebody might be able to get them. Okay, you can create your own digital certificates. If you have the Java SDK, the software development kit, or the Java development kit, then you can, it has tools with it, and you can make your own certificates. It's very easy to do. There is also tools for Microsoft to make your own certificates. KeyTool is the one you want to use. KeyTool, as the name implies, allows you to make keys. There's JarSigner, which is a tool in Java. Java has files called jars. They're just compressed files with a bunch of classes in them. But the JarSigner tool will take a key made by the KeyTool and a jar that you created, jar tool, and sign it. So it has the digital certificate in it. And so when you get the jar, you can validate that, in fact, the classes are all correct and nobody's corrupted them. Documentation out there online from docs.oracle.com. Java version 20, I think, is the latest one. You can get that out there. It's a long, go to this website, it's a long list of tools. They're in alphabetical order. It turns out that KeyTool is way near the bottom because almost everything begins with a J. You gotta think, okay. When you use these tools, they talk about something called a key store. A key store is just a file where they're storing the keys. Keeps the keys and stuff. It's usually encrypted for security. When you create one, you'll give it a key. It's just a file. Often it's a file without an extension. So here is some use of the KeyTool to do this. So you're going to use that. You got the KeyTool GenKey pair. It says I want to generate a pair of keys, a public and private key. Alias, that's giving it a name. Where I want to put this. This is the name of a file I want to put this in. this is the password I want, and I want to encrypt this with the RSA algorithm. And so again, your last name, you can give it any name for reasons of, it's easy to use your last name. Class cert is just a file name to place it, and the secret key is some key you want to use. All right. Now, great risk of causing a problem. You should never do live, live demos. I'll warn you that live demos have all sorts of problems. Things never quite work the way you want to, but I'm going to try one anyway. You don't see the live demo. Why don't you see that? Online, they see it. Hang on. Hang on, we're going to have to. Come on, stop out there. Slideshow. Usually that's unusual. It doesn't want to go away. Well, okay, hang on. I'm not defeated yet. All right, there we go. All right, sorry, that was more difficult than I wanted to do. You'll notice down at the bottom, which I have the key tool thing, pretty much copied it from there. Let's see if this works. And yes, all right, it did something. Let's see what it did. I, again, did the key tool, generate a pair, give alias Williams, supposed to be a space in there. Let's try this again. Okay, backing up. Space. Okay, try it again. Enter. All right, work this time. It's going to ask me for my name, so I'll put my name in there. Name of the organization. You can, of course, put whatever you feel like here. Where are we? We're in Greensboro. This information will appear in the certificate, and it's basically just to provide information to somebody who uses the certificate. Who is this? Where does it come from? Okay, this is valid. Why, yes, it is. And then, okay, it has generated a self-signed certificate. Yes, self-signed, because I signed the certificate myself. It's not approved by any certificate authority. You can get one. It's got a validity of 90 days. There's the information I gave it. It's a 3072-bit RSA key pair. Okay, RSA algorithm. So now we have that. If we make this smaller, okay. Stop sharing again. Let's. How do I get out of full screen mode with this thing? What? I need to get back to Windows. I don't want. I have full screen Zoom, and I'm trying to get out of it. Makes it very hard to open up something I didn't have already opened.
You can hit escape.
Skip,
Yes.
where is Skip? Oh, escape. Oh,
Yes.
I pressed that. I don't know how many times I pressed escape and it didn't work. Okay, thank you. Out there. All right. Let's go to my desktop where I had everything. Yes, and there. Where is it? It was in dark. Oh no, back to desktop. Where is this? This is temp. Temp.ert. I'm sorry, I got lost. It happens sometimes. Temp. ERT. I meant to be cert, but I misspelled it. There is the key. Okay. That's the key. Now, I'm going to go into Chrome. Oh, you guys can't see this. Let's back to Zoom. We will share the screen. We're going to do the whole screen. Okay. Hopefully you can see everything. I'm here in Google. I'm going to go up to the little dots. Say I want to go down to settings. I want to go over to privacy and security. I want to go down to security. And then I scroll down here to manage device certificates. There we are. And I go import. I want to import a certificate. Okay, we're going to import one. Where did I get it? Well, I put that, right there. It didn't have a name, so I'm going to go for all files. There is that file. Click. Open. Next. Password. Oh, shoot. Where did I call that password? Okay. Password was secret. Of course. Wouldn't take long to break that one, would it? Secret. And then, next. Place it in personal. Next. Ready to go do it. The import was successful. And now, yes. There is a key out there that I just made that's good for 90 days, which is up until December 12th. We have a key. And now I can do other things with it. If I wanted to sign a Microsoft Word file, let's just do that. Let's get really crazy here. Out of the way. And we'll go to Microsoft Word, wherever Microsoft Word is hiding. There it is. Create a blank file. This is a test. And we'll save that someplace. We'll be able to find it again. I'm going to save it. Where I put the other stuff. We'll call it, this is a test, is a nice name. Okay, now I'm going to sign this Word document. I go up to File, Info, Text Document, add a digital signature. Cool. Commitment type. Well, I created this thing and I approve it. This is a demo. I could provide details, but I'm not going to. What certificate should I use? Show me some more. And here's the one I just created. We'll use that one. Okay. Oh, yes, it can't be verified because it's self-signed. I don't care. I know that. Sign it. It's been signed. Now, more messages. If I go back up here, it says mark this final. That is final. Oh, just like final in Java, another programming language means you can't change it. This document cannot be changed. Now, if you do change it, it'll invalidate the digital signature. So now this Microsoft Word document has been signed. I can send it to somebody and they would see that it's been signed. Now it's been signed by a personal certificate, a self-signed certificate. So nobody's authenticated it, but you can see that it's signed. And anybody changes it, yes, you had a question. Yes, if you copy this file, I tested that this afternoon, just to make sure, because I thought about that. Yes, if you copy the file, yes, the copy is signed. And you can modify one, and then the signature doesn't work with the original, it'd still be good. So you can copy. Okay, everybody got that? I'm glad you, I hope you do, because the assignment out there requires you to sign some files. Yes, you have a question?
So, let's say you want to send that file to someone, so the other person will have your copy.
They'd have the key,
Yeah.
it comes with. Yes, okay, oh, go away. I'll skip this for now, but yes, there is an assignment due on Tuesday at noon. It requires you to create a certificate or buy a certificate or get one for free, sign a document, anything. Sign a jar file or a Microsoft Word file or an Adobe PDF file or whatever you like. I don't care. Upload it to Blackboard. That's part one, good for 34 points. Part two is just a bunch of questions about if Fred is a member of this group and he's a top secret person, what access does he have to this file? You've seen those before. That's it. So they're all due. And there's a, that's, we want to do that sort of stuff because there's an exam a week from today. It's available all day. It's online, even for the people who normally come in person. This is an online exam. It starts at 6 a.m. in the morning, goes to midnight. No, you do not have to spend 18 hours in the exam. Please don't. It should not take you more than 2 hours. In fact, please keep track of how long you spent on the exam, because I'll put out a survey and find out how long my exam is. I want, sometimes I'd like to know, how cruel am I? How long did it take you? Check that out. It shouldn't take long, but I like to give people a long time to do it because some people have jobs and they have to do it at times. Okay. You can go in and out of it. And once you start, you can pause, come back, do it again, change your mind. Okay. Of course, it's open book and open notes, because how do I know? Fine. Questions about the exam or the assignments? Yes, sir. On the exam? I don't know until I get tired of making them. There will be some lengthy questions, like signing something would be a long question, worth more points. This takes time. Questions about if Bob's top secret and he wants to access, those are easy. Those are multiple choice. They aren't worth a lot of points. Usually there'll be about a dozen of those multiple choice things because they're just a giveaway. And then there'll be some activities that are longer. Do something, send me the file. Yes.
So the quiz is to like this.
Exactly. Yes, the quiz is out there to look something like the exam. Something like, no, exactly. No guarantees that if I can think of something mean between now and next Wednesday, well, I'll put it on the exam. Quiz is due Tuesday at noon. You should know Tuesday at noon. By then, you'll be able to go back to Blackboard and see your answers, see what's right, see what's wrong. It should tell you what's wrong. Hopefully, if Blackboard works correctly. If it doesn't, let me know. Every now and again, Blackboard doesn't always do what I ask it to. And of course, the signing, you'll know if you signed it all right. It tells you it's signed, and I'll know. Another question. No timer on the, oh, no, I go. Just take as long as you like. Take as long, yeah, well, take as long as you like. Not more than 18 hours. Yes. There's multiple ways to make certificates, and I'll put some of this information on my website, the Comp 422 Comp 620.online website. I have pages that aren't there yet, but it was my intent this afternoon, got very busy. And I didn't get that done, but I'll try to get it tonight. I have instructions on how to do all this. It's in the. No, it had been my thought that I was going to ask you to crack into the pet. There were so many weird difficulties with that. I'm not going to do that. That had been my intent. Keep that. I told you to keep that software. I was going to use it for the exam. But some people have some of the strangest errors I ever saw. And it would be unfair to put that on the exam when these strange problems may exist. So kills that idea. Question out there, yes, sir. Yes. So, but I'll have the answers out there so you know how you did. Okay. Other questions? And that's it. Again, tonight I'll put some more documentation on the website or Blackboard on how to do all this, but it's all on Zoom that you can see on the, on YouTube tonight.
One last thing.
Yeah.
The quiz, what had, short, was, you tried to do a short.
Short answers and multiple choice. It may have long answers if I can think of a good long answer question. Okay. That's it for now.
Professor Williams, where are you located in the building?
Right now, I'm standing in Graham 208.
Oh, wait. Okay,
You coming or should I run for it?
I'm coming.
Okay, I'll wait for you.
Thank you.
Anybody else have questions? Okay, I'm gonna terminate this.